Hey, hi, good morning, everyone. Good morning, friends. Welcome back to our session on artificial neural networks. So, we have successfully understood the conceptual part, starting from the introduction of neural networks, then, how a neural network works, and the steps as part of the training a neural network. And, we also understood the activation function types. And in the previous session, we understood how gradient descent optimizer helps to update the weights and bias. We also understood the types. So if you haven't gone through my previous sessions, so friends, this is a sequence of sessions. We are doing it as a playlist. So, you know, as a continuation part, just go through the previous sessions so that you'll understand the project that you're going to discuss today in today's session, right? So in today's session, we are going to understand, we are going to perform a project, okay, to predict whether it will rain tomorrow or not. Okay, so I'm using neural networks. Okay, and the ID that you see here is I'm using Google Colab. So far, in all the playlists and all the different sessions that were covered so far, we are using only Spider. But as a change, I would like to use Google Colab as well. So, if you see the UI, it's similar to a notebook where we have cells. So the Python code doesn't change. It remains constant. But additionally, you'll observe the change with respect to the user interface. So I hope the agenda is clear and let us get into the session. So friends, before I start the session, before I start the project code, this is the data that we are going to work. The same thing we have, the same data set we also used for logistic regression. So you see, these are the inputs that we have, and we are going to predict whether it will rain tomorrow or not. Okay, so we have the records, and it's around 25, 2,55,000, right? So these data we are going to consider, and I'm using neural networks to train the data, and I'll be successfully predicting it. Right. So, first I'm going to install feature engine, a package, a library. In order to work on outliers, I need a library called feature engine and I'm installing it. And, if you are using any notebooks, for example, it might be Google Colab or Jupyter Notebook. You're supposed to use exclamatory mark in front of the command, in front of the pip install command, package name, whatever the command, you are supposed to use exclamatory mark. And I'm going to install feature engine because I don't have it. So you see a play button. It helps us to, execute that particular cell. If I want to execute this cell, I'm supposed to click on this play button. So it is also displaying the time that took for executing a cell, the current cell. So seems like we already have, right? So no issues. Now what I'll do is I'll go and import the required libraries. Whatever the libraries that are required for me, I'm importing them all together in a single cell. Okay. So, but before I execute, we also have a shortcut to execute the cells in Collab. Either you can click on Shift and Enter together. By pressing Shift and Enter together, you can execute the cell. If not, we also have, runtime. Okay, under the runtime option that you see in the top left, so we have run all. That means all the cells will be executed one by one. Then run selection. So if you are going to select any code and if you want to execute that particular code, yes, you can also execute accordingly. But I'll not use these options that are available here. I'm going to use shortcuts, friend. Okay. So let us discuss the libraries that we are importing. I'm importing pandas library. Pandas library is for data manipulation. Then what am I importing? I am going to import Winsorizer for handling missing, outliers. My bad. If you had any outliers in the data, that has to be treated, and we can treat them using Winsorizer. Then next to Winsorizer, I'm going to import simple imputer, and simple imputer helps us to you know uh, perform imputation. If I want to handle missing values, I'll import simple imputer, then I'll handle the missing values as well. And together, I'm also importing min-max scaler and standard scaler for feature scaling, and one hot encoder for performing encoding tasks, right? And finally, I'm importing pickle to save and dump the model, and train test split for splitting the data into train and test parts, not to partition a data into train and test. I'm going to import train test split. Then confusion metrics, accuracy score, and classification report. So together, I'm going to use all these three metrics. Okay, I'm importing them as part of sklearn. And I'm also importing warnings. Okay, so in order to have a clear output, I'm suppressing the warnings by importing them. Okay, so I'm executing this cell, and let us import all the libraries. It's done. Okay, it says that we are done. Now let me load the data set, because the data is, no, we should have it in the Python's memory, right? So we have the data set in a CSV file. Since you are going to use collab, ensure this particular, CSV file is also present in the folder. Okay. So I'm using read underscore CSV function, and this particular, I'm going to pass the path. So let me open here. You see here, I initially uploaded the file. Okay. So this was uploaded into this files, and I have copied the path from here, and that specific path is what I'm using. And this will ensure that the content which is present in this, or the data which is present in this file, is read and stored in DF. So I want to have a look at the data. Let me execute it. So when I say DF, it returns me the data. But if you see only the top five and the bottom five records, you're able to see, because it's impossible to have a look at all the 254,000 of column, rows. Making sense? So this is the data on which we are going to build a neural network, train it, and successfully we are going to make some predictions. Then I'm using shape attribute. So df.shape will return as the dimensions, the size of the data. So as we are aware that we have 254 records, 54,000 records, and there are also 19 columns. Yes. So this is the shape. And now I want to get this, the null value count. What is this count of missing values present in each and every column? I'm using isNull function. This isNull function, it goes and checks each and every cell of the DF. Okay. And it returns either true or false. Since I'm using isNull function, it returns either true or false. So you know that in Python, false is interpreted as 0 and true is interpreted as 1. When I use dot sum, it aggregates all the values of false and true, and it is going to return us the count for each and every column. So seems like location column does not have any missing values, but I see missing values in all the rest of the columns. And here is the count. I hope it's making sense. Let me execute. So this is, the missing value count. Now I can clearly see there are also missing values in my output, and it's around 7,804. 4 records in which we have missing values or null values in our Y column. Now, what I'm going to do is, let me drop the null values that are present in the Y column. Wherever we have the null values, the missing values in the null, Y column, rain output, I'm going to drop those records. Okay. Then again, I want to get the count in the new data, in the clean data for all the columns, and I also want to get the shape. So in order to understand this better, probably, I'll take this particular line of code into the next cell. So that would make sense. Yes. Now let me you also use print function. So whenever you use print function, it allows us to, print the data output to the console. Right. So let me execute it. You see, do we have any missing values in your Y column? No more. No missing values in our Y column as we are dropping them off. Right? Yeah. Then, and if you see what is the shape of the missing, the clean data set, what is the shape? It says 2,46,554 rows and 19 columns. Then, on this clean data, I would also like to get the value underscore counts function performed. So value underscore counts function is going to identify the unique values, and it returns the count of each and unique value present in this column. Okay. And the result has to be stored in this variable. And I'm going to print that particular variable. Let's see what is the count of each and every class. Oh my God. You see, it is clearly showing that under the rain tomorrow, we have only two values, no and s. And what is the count for no? It's 1,92,019 rows. And for yes, it is 54,535. So what do you say? Do you say is it balanced or imbalanced? Okay, friends, if you feel, if find it as balanced, you know, in the comments, mention it as balanced. And if you feel it as imbalanced data set, mention it as imbalanced in comment section. Making sense? Now, what am I going to do? I'm going to, take the same data set on which we have removed the null values from the Y column, and I'm separating the rows of no and s. You are aware that there are two classes, no class and yes class in our Y column, and we are going to separate the records for two different classes. So if the Y column holds no, if the value under the Y column is no, so those particular rows will be part of no underscore rows. And if the values under the Y column are yes, thus the particular rows will be part of yes rows. So let me click on it. Let me execute. It's done. Now, I'm randomly sampling the data. Okay. So from this no rows, I would like to get only 22,000 records. That's enough. So I'm using a sample function. So this sample function is going to do random sampling, and random underscore state is equals to an integer. This represents, so if you're running the same code for multiple times, you're supposed to get the same records. If not, the output gets changed. So here, I'm going to perform sampling, right? So sampling is done randomly. So if I run now, I'll get some certain number of records, 22,000 records, randomly from 1,90,000 records. Yes. But after some time, if I run the same line of code, I should get the same records that are generated now. If not, my output will get changed. My output changes. So for that reason, we use random state as a parameter, and this random state ensures to produce the same records as it is. So we set the random state for reproducibility. Okay. In the same way, we are also generating sample records of 30,000 from yes rows data frame, and and finally I'll concatenate no sample rows and s sample rows together. They'll be concatenated. It's nothing but you're combining the rows of no and yes. Then what are you going to do? You're going to reduce the sample. Okay, so you're shuffling the combined data frame. Okay, again, this is an optional step, but anyhow, let us perform it. So I'm going to shuffle the data, and I'm also going to get the shape of, before the shape, I'm going to get the value and the counts in my Y column after concatenating. So it's clear that we have 30,000 records with yes and 22,000 values with no. Making sense, right? Why 30,000 and why 22,000 value? Because of the number that we have specified as part of our code. Now, let me also get the shape of the reduced, the one that we have reduced. Anyways, we got it over here. Then let us get the info function applied on it to get the information about the data set. Then let us also get the columns. Okay. And finally, let us drop the location column, which is an irrelevant column for us. Let us not use it as part of our, model building part. We'll drop it and get the info function done once again. See. So this is the info function that was applied to the data frame before dropping location, and this is after dropping location, right? So it clearly says that we have these many null values under each and every column, and the data type, okay, for all the columns. Now, let me separate inputs and output. So we have inputs and output combined in this df underscore reduce data frame. I'm going to separate both of them. Okay, so from df underscore reduced, if I just remove rain tomorrow column, I'll have all the inputs. And if I just take only rain tomorrow column from the same data frame, I'll get my output. Then once after separating my, inputs and output, then I'll get the null value count in each and every, data frame X and Y. And from X, I'm going to get only, I'm separating numerical features and categorical features. And let me print all these numerical and categorical features. So probably, you should use print. Only then it allows you to give the output. So in inputs, in the X data frame, so we have the inputs in which these are the numeric columns, and in inputs, this is the only categorical column. This is the only categorical feature. Now, I'm going to get the null values. I'm going to check the null values, especially for the categorical features. So we have rain today as the column which has categorical features, right? Let me calculate, or let me get the count of the null values in the column categorical feature. And if it has any null values, I'm going to use simple imputer function to handle the null values present in the categorical column. And I'm going to use the strategy as mode. Okay, most frequent represents mode. Once after initializing simple imputer, so I'll use the function, okay, which is stored in imputation, and that particular function gets fitted and transform the results of the categorical features. Okay, so once after fitting and transforming the results, you will not observe any kind of, null values. So what I'm doing is I'm converting back this array to data frame by passing the column name. And to this output, I would also like to perform encoding. And this encoding will be done by one hot encoder. So one hot encoder helps us to perform encoding, which means converting non-numeric data to numeric data. Then once after initializing one hot encoder, I'll fit on the data and I'll get the transformer results. In the same way, this particular array, I'm going to convert back to a data frame, and the data frame will have the columns that we get from here. And finally, I would like to get the head function so that we'll quickly have a look on our output. So there are only again, two values under the rain today. It is no and s. It is no and s. So I got two columns. It's no and s, and the values are encoded. Done. Now let us, explore the numerical columns in the same way. Okay. So initially I want to check the box plot because, even though if we have null values, the missing values, the strategy that we are going to apply should be depending on the outliers that we have in the box plot. Okay, when we visualize a box plot, if we have outliers, probably we are supposed to, go with median imputation. And if we don't have outliers, we go with mean imputation. All right. So seems like we have outliers. So I'm going with median imputation. And once after performing median imputation, I would like to apply, once after initializing the simple imputer, so that particular function will be applied on the data and we'll get the transformed results. So this particular array gets converted back to a data frame using data frame function from pandas, and we are going to store the output in numerical underscore features underscore imputed. So to cross check, I'm again using the same logic isNA.null, isNA dot, isNA function dot sum function. So this will ensure whether there are null values even after applying simple imputer on the inputs, numerical inputs. Okay, seems like we'll not have any null values. Now, again, I'll plot the box plot for checking the outliers to visualize the outliers. And the method that I'm going to use is winsorization. And the winsorization, the capping method I would like to keep is Gaussian. And, I'll go with the tail. At both the tails, I would like to treat the outliers. And the fold, I'll just keep it as 1.5. And I would like to pass all the list of numerical features. Okay, once after initializing Winsorizer, it gets fitted on the inputs and we'll get the transformed results, and they are saved in this variable. And finally, we are going to plot a box plot on this, results of winsorization. Okay, so once after handling the outliers, I'm going to use standard scalar for performing feature scaling, and I'm initializing standard scalar with the default parameters. So what is the formula for standard scalar, friends? What is the formula for standard scalar? Z is equals to x minus mu by sigma, where the output will be for all the columns, mean of all the columns will be 0 and standard deviation will be 1. Once after initializing standard scalar, I'm going to fit on the data and I'll get the transformed results, and those will be saved under a variable clean underscore numerator. And this particular array I'm going to convert back to a data frame. And finally I concatenate both numerical and the non-numerical features output, and I'm going to get the head function. Right? So I'm going to get a head function calculated on the final features. So this is going to print the head function. And also, let us convert this S and no that we have to 0 and 1 in our Y column. Okay. So in Y column, we have S and no, right? Whether it will rain or not. So these numbers, the categorical values that we have, we are going to convert back to numbers. S will be replaced with 1 and no will be replaced with 0. So anyways, I'm going to use map function. So mapping will be done. Let me execute this and print the output. So it's done. So these are the box plots, initial box plot. Okay. So once after completing the initial box plot, we also checked it twice. Okay. So this is how we have the output. So far, we just completed only data pre-processing, friends, right? We did not go with the model building part. We just completed only data pre-processing. Now, what I'll do is I'll start the model building part. Okay. So as part of CRISP-MLQ, we have in total 6 phases. So we have completed phase 2 so far. And let us go and start the third phase of CRISP-MLQ. It is model building. What do we do as part of model building? Model building is a step of, it is a phase of CRISP-MLQ, which helps us to build a model. Since I'm using artificial neural network, so let us go and build a neural network, a basic neural network using the data, and let the historical data be trained as part of the training process. And let us also get the predictions and calculate the metrics. Right. So you see here, what am I going to do? I'm going to split the data into train and test. Okay. So I'm going to use train test split function. So this function, excuse me. So this particular function helps us to split the data into train and test, data. We'll have train data and the test data post executing this, line of code. I'm passing all the final features and y together, where I would like to get the test size as only 20%, and the random state I'm going to use for reproducibility. The same concept, friends. Wherever you're going to use random state, so that means for reproducibility, you're going to fix a random state to a integer. So just remember it in this way. Okay. And what are the 4 parts that you're going to get? I'll get X train, X test, Y train, and Y test. So nothing but train data inputs and train data output, test data inputs, and test data output. So, so these are the 4 inputs that we are going to have as part of train test split. Now, once after splitting the data, let me execute this. Yep, done. So once after executing this, let me go and import some of the important libraries to build a neural network. Okay. So for that, I'm going to use, I'm going to import TensorFlow and Keras libraries. Okay. So we have TensorFlow and Keras explicitly designed for, deep learning applications. Okay. If you want to build a deep learning application, so we are supposed to use TensorFlow and Keras. So we let us go and get habituated of using TensorFlow and Keras from the basic neural networks itself. So friends, I'm importing TensorFlow. It is a deep learning framework, okay, which is generally used to build any kind of neural network. I'm importing the entire library. Then from TensorFlow.keras.models, I'm going to import sequential. So this sequential is a function which helps us to build a sequential model. Okay. It builds a simple basic model, okay, which is sequential. Then we are also going to import dense and dropout from same TensorFlow.keras.layers. Okay. So dense helps us to create a fully connected network, and dropout is a hyperparameter. It's a regularization parameter which helps us to prevent overfitting. Okay. I'll talk about dropout. No worries. Then as part of optimizers, I'm going to import SGD, stochastic gradient descent, ADAM, and RMS prop. So what is the purpose of using optimizers, friends? So optimizers helps us to, you know, minimize the loss function, and it when we use optimizers, we are going to achieve the local minima for a cost function and we are going to get the best weights. So for that purpose, I'm going to import SGD, Adam, and RMS prop as the optimizers. Then I'm also going to import some callbacks like early stopping, reduce LR on plateau. So it's nothing but reduce learning rate on plateau. So I'm going to import some kind of, callbacks. We'll discuss what is the purpose of each and every function. Let us discuss as part of, the steps. So it's under execution and done. Now let us start, defining our neural network. So the first step is to build the model. I'm defining the model. So what I'm going to do, I'm using the sequential function that we have imported from tensorflow.keras.models. So this will help me to build a simple base model, a neural network, which is sequential. Okay. So let me start adding layers. So I'm going to build the first layer, friends. Okay. I'm going to start the first layer. So where I would like to have to this model that got initialized, I'm going to add a dense layer with how many neurons? 64 neurons as part of my first hidden layer. So units represents the number of neurons, and the activation function that I am going to keep as part of the first hidden layer is ReLU. What is the function activation function ReLU does? It uses the formula max of a comma 0, 0 comma x. So if the value of x is greater than 0, it returns x as it is. If the value of x is less than 0, it returns 0. All right. So we understood the types of activation functions in the previous session. So friends, if you haven't gone through my previous sessions, do watch activation functions and its types that I have covered in my early sessions. So this ReLU is overcoming the problem of vanishing gradient descent, as well as, it is not computationally expensive. It is just using a basic formula. It is max of 0 comma x. So it is not computationally expensive. And, we can use ReLU and its variants as an activation function in our hidden layers as activation functions, right? And with respect to input layer, so as we have 18 inputs, so there should be 18 neurons. I hope it's making sense. So this is how we are going to build the first layer of the hidden layer and the input layer together. Then to the same model, I'm going to add dropout, and the dropout value that I'm passing is 0.2. What is this dropout? Dropout is a regularization parameter that we add as part of neural networks. So this dropout helps us to, drop random neurons across the training journey. Okay. So this is going to prevent overfitting. When you don't add dropout to the neural network, what happens is, so across each and every epoch, if the same neuron gets trained, what about the other neurons? So this actually leads to overfitting. So when you add dropout, when you are going to assign a value for your dropout, this will ensure that randomly, this percent of neurons will be dropped randomly from that particular layer. So that means 20% of the neurons from this first layer, hidden layer, will be dropped from each and every epoch. Okay, so that doesn't mean every time the same neuron gets dropped. So this will ensure that the complex patterns will be learned by each and every neuron present in the layer, right? So that is the benefit of using dropout in our neural network. Then let me also define the second layer, second hidden layer. So I'm going to add a dense layer once again. So dense function helps us to dense is going to create a fully connected layer. It's going to it's going to create a fully connected network. So if you have one neuron present in hidden layer, that particular neuron will be connected to all the rest of the neurons in the previous layer. So dense helps us to create a fully connected network. And how many neurons are we going to have as part of second hidden layer? It is 32. Okay, it is 32. Then what is the activation function that I'm going to use? It's again ReLU, and you know, I'm just using the same dropout value. It is 0.2. So there is no change with respect to the dropout, friends. I'm just going with the same dropout value. Then let me also come up with third hidden layer. I want to add one more hidden layer to my neural network. So this time I would like to keep only 16 neurons and the activation function as ReLU. Okay. So this is how we are going to add hidden layers in our neural network. And finally, let us go and keep output layer. So to the model, let me add a dense layer in which we'll have only one neuron in the output layer, and the activation function that will be used is sigmoid. Why sigmoid? Sigmoid is the activation function that is used for binary classification task. Excuse me. So I'm using sigmoid activation function for binary classification. So the project that we are working on, brain prediction, is having only two classes. So let us go and use sigmoid activation function in our uh, output layer neuron. Now, once after defining all the layers, input layer, hidden layer, and output layer, so I'll go and compile the model. For compiling, what I'm going to use, I'll define my optimizers. So you see, I'm going to use Adam optimizer. So without an optimizer, you cannot expect the loss to be minimized. So in order to reduce the loss, what we have to do? We are supposed to use an optimizer that will ensure the weights get updated, the bias get updated across the journey of the training, and will get a minimal loss. Where I'm initializing the learning rate, the eta value to 0.001, a small value. Okay. And the loss that has to be considered is binary cross entropy. I hope you remember, friends. We discussed loss function and cost function. So for a binary classification task, the loss function that is generally used is binary cross entropy. And the metrics that we should be considered is accuracy. So this is how we write the compile code for compiling the model. And let me get the summary of the model. So let me execute this. Okay. So under each and every layer, we have the neurons. Okay. What is the shape, the parameters, and parameters represent the weights. Okay. In the same way, after the initial layer, we'll also go to the second layer. So the dense and the dropout. Okay. These are the parameters, and what is the parameters at each and every layer we have as a summary table. So this is just because of the summary function, friends. Okay. So as part of summary function, we have the table over here. So it's representing the shape and the parameters. All right. Now let me define the code for training. So once after defining the model, this particular model has to be fit on the trained data. Solute fit function where I'll pass X train and Y train, the input features and the output features, in which I would like to have an validation data of 20%. So if you have 100 records in your training data, and if you keep the validation data as 20%, so only 80 records will be used for training and 20 records will be used for validation. Okay. And what is an epoch, friends? Epoch represents, you know, when the model, when we are going to pass one complete forward and backward propagation for the entire data sets represent a epoch. So I'm going to have 100 epochs, okay, so that the entire data will be passed for 100 times. But will it pass for 100 times? No, because I'm coming up with an early stopping. What is this early stopping? We'll understand. But before that, we have batch size. This batch size tells us each and every batch will have only, 32 records. Okay. So 32 records will be sent as a batch, okay, of size 32. And in this way, the number of batches will be decided per epoch. In total, we have, if you have 1,000 records, accordingly, the number of batches will be measured. And finally, I'm also defining my callbacks where I have early stopping function to monitor the validation loss. So the validation data that we have took, okay, if it is going to monitor the validation loss, and if the patient is less than 25%, you know, it has to return the best possible weight. So that means, you know, the model training before completing 100 epochs, if the monitor, it monitors the validation loss, and if there is no change with respect to this validation loss, the model stops without completing this 100 epochs. So that is the purpose of using early stopping. It is also used to perform to avoid overfitting. Okay. So let me execute this one as well. I'll show it to you. One and each and every epoch, it takes time. Okay. It is displaying the accuracy, the loss, the binary cross entropy, the loss, the validation accuracy, and the validation loss. I hope it's making sense. So for each and every epoch, this is for first epoch, then the second epoch, third epoch, and so on. So if you observe for epoch to epoch, what's happening, you see some gradual increase with respect to the accuracy and a gradual reduction is with respect to the loss. So in this way, it starts epochs. I hope it's making sense. So just try building a small neural network, on a structured data, and, understand the concept, how ANN can be used in real time. See, it's taking time, but, as of now, it's going very fast because average epoch, each and every epoch is averagely taking 3 to 5 seconds of time. That's it. Max. That is a maximum time that is being consumed by every epoch. Going in a good way. 35 epochs are done, and the accuracy is around 80%. Let's see how many epochs it is going to consider, because we have used early stopping, right? So this early stopping is going to monitor the validation loss, and if there is no significant change with respect to the validation loss, it stops, the training journey. Let's see how many epochs it is going to complete. Done with 55 epochs. Is it done? Yes. So if you see, as there is no deduction with respect to the validation loss, it stopped at 57th epoch itself. Okay. In general, it has to go till 100 epoch, but since we are using early stopping, you know, it has stopped. It has considered the validation loss and the patience was being calculated, and it stopped. Now let us use this particular model and evaluate on the test data. Okay, I'm passing both inputs and output to get the test accuracy and the loss. Okay, and let me also print them. So test loss is 0.44. So test accuracy is 0.78. 78% on test and 80% on train. So the model that we got is a good one because the accuracies are close to each other, and moreover, in general, if we are able to get 80% of accuracy in real time, that's again a good model that we have built, right? So I hope this particular project had given us a lot of understanding with respect to the neural network, how a neural network is built using TensorFlow and Keras libraries. And I would like to tell that in the future sessions, in the coming sessions, I would be doing, uh, playlist on convolutional neural networks as well as recurrent neural networks. So this marks the end of artificial neural network. So friends, I would like to tell one more thing. Just not listening to this class, just not listening to this particular session. Do also, do hands-on. Take a data set, you know, train the model, train a neural network, and see, pass the same epochs, see how it is getting trained, and also see the accuracies, compare the accuracies, whether you're getting a right fit model or not. So that's all for the day, and we'll meet in the next session. Until then, take care. Have a great day. Signing off. Bye.